Interfacing of analog to digital converter with 8051. Let us understand the pins of IC 0808 or 0809. This IC is 8-channel IC, so it has 8 analog signals, 8 analog channels, IN0, IN1 up to IN7. User can connect analog input to this 8 channels, and IC will convert this analog signal into digital. These channels are internally multiplexed, so at a time user IC will select only input from one channel and convert it into digital. Now to select a particular channel, the IC has a address lines for this channel. So each channel is having unique address and user has to send address of particular channel on address lines A, B and C. So here it is shown the addresses for each channel. So IN0 channel address is 000. For IN1 address is 001. Similarly for IN7 address is 111. After placing address of particular channel on address bus, user has to latch this address. So for that, ALE signal is used. It is address latch enable signal and user has to give low to high pulse at ALE terminal to latch the address. Once address is placed on address bus and it is latched, now user can send a start of convergence signal. Here it is shown as a start signal. So again user has to give here low to high pulse at start of convergence signal. Now this IC will start conversion of analog input into digital. Now user can check whether conversion is complete or not using EOC signal, that is end of conversion signal. Initially, EOC terminal will be at logic 1 and when conversion is over, it will be at logic 0. So user can continuously check whether EOC is 0 or not. If it is 0, it indicates that conversion is over and digital output is stored at the register of internal register of this ADC IC. To place this converted digital output on digital bus, user has to send output enable signal, that is OE signal. So low to high pulse should be connected to OE signal to place this digital output on digital bus or data bus. So it has 8-bit digital data bus. So D0, D1, D2 up to D7 is a digital output terminals where output will be available after giving low to high pulse on output enable terminal. Now for operation of this IC, we need a clock signal. So here user can connect, user can use external circuit to generate a clock, or user can connect the clock signal of 8051 to this clock terminal. Then it has VCC terminal where user can connect a plus 5 volt supply and ground terminal GND should be connected to ground. Now two other signals are V reference plus and V reference minus. V reference minus we are connecting to ground and the positive supply voltage, positive voltage should be connected to V reference. Detail about V reference we'll see in next slide. So go to the all important signals of this ADC IC. It has 8 analog channel. Then to select the particular channel, it has address lines A, B and C. Then address latch enable signal is there to latch the address of particular channel. Then start of conversion signal to start the conversion of analog into digital. Then to check whether this a conversion is over or not, it is having EOC signal, and to place a converted output on digital output lines, it has a OE signal, output enable signal. So after giving output enable signal, digital output will be available on digital output lines D0 to D7. Then we have to connect VCC and ground. V reference, that is positive voltage, and V reference minus should be connected to ground again. Let us see relation between input, analog input and digital output. Now it is 8-bit ADC. So step size for ADC is 2 raised to power 8, that is 256. That means 256 output steps are there. So digital output we can get is from 000000000 to 11111111. So total 256 steps are there for digital output. The step size, that means how much analog input should change to change a digital output by one step. So that we can compute using V reference divided by 2 raised to power 8. So size of step is depends upon the V reference. Now if we consider V reference is equal to 2.56, then step size will be 2.56 divided by 256, that is 10 millivolt. It indicates that if input analog voltage change by 10 millivolt, output will change by one step. For example, suppose input analog voltage is 0 initially, so output digital will be 00H. And if input changes to 10 millivolt, output will change by one step, so it will go to next step, that is 01H. But we can compute the decimal output using formula V in into 256, that is 2 raised to power 8 steps, divided by reference voltage. So that is in our case V input voltage into 256 divided by 2.56. This reference voltage can be up to 5 volt, that is supply voltage. So let us consider example. So let input voltage, analog input voltage applied is 1 volt. Then output from this formula will be 1 into 256 divided by 2.56. So this in decimal output is 100, and we'll get a digital output that is in binary form. So we'll get output like this 0110 0100. This output will be displayed on LCD. If input voltage is 2.56 volt, then output is 2.56 multiplied by 256 divided by 2.56. So that is 256 in decimal. If we convert, we'll get FFH. So this is the final value. All LEDs will glow. So using this, we can compute the output digital voltage for every input voltage, analog voltage. Let us understand the interfacing diagram of ADC with 8051. Here we are using channel 0. So we can connect the output of any analog sensor to this channel IN0. Here simple voltage divider arrangement is shown. So you can use here pot to vary this analog input at channel IN0. So we are connecting analog input at channel 0. The output data lines, digital lines D0 to D7 are connected to port 1, P1.0 to P1.7. The address lines ABC are connected to P2.0, P2.1 and P2.2 respectively. The start of convergence signal is connected to P2.3 and ALE is connected to P2.4. The output enable signal is connected to P2.5 and end of conversion is connected to P2.6. Clock, we can connect here clock from 8051, or if you want you can use any external circuit or clock generator to connect clock to this IC. VCC is connected to 5 volt supply, and to adjust V reference voltage, here this potential divider arrangement is used. V reference is connected to ground. Ground terminal is also connected to this ground terminal. To display the digital output, this port P3 terminals are connected to LEDs. So we can connect here 8 LEDs, one to each port pin of P3. Now, algorithm for this writing ADC program. So first, since we are using port 1 and pin 2.5, that is end of conversion terminal, as input to 8051, to protect these pins, we have to send logic 1 on each of these pins. So we'll send the logic 1 to all pins of port 1. That means we have to send FFH on port 1, and we'll send logic 1 on pin P2.5 so that we can protect these pins since we are using these pins as an input pin. After that, manually we have to connect analog input signal to channel IN0. The next will send the address of channel. So since we are using channel 0, the address will be 000, that should be placed on ABC terminal. Next is send address latch signal, ALE signal. So low to high pulse. So first we'll clear that pin and then we'll set that pin. So this signal we have to send on ALE. Then next is start of conversion signal. Again low to high pulse should be connected to SOC terminal. Then we'll wait for end of conversion. So we'll check whether this is 0 or not. If it is 0, then we'll go to next step. That is, we enable the output enable signal, that is low to high pulse. Again we have to send. After that, the digital converted data will be available on port pin P1. So that will send on port P3. So we'll read this converted digital data from port 1 and we'll send it on port 3 where LEDs are connected. The program is simple. First, we'll send a logic 1 on all terminals of port P1. So we'll use instruction move P1, comma hash 0 FFH, and P2.5 also we want to send logic 1. So use instruction set bit P2.5. So we want to protect these pins as we are using these pins as a input pin. Then we'll send the address on ABC. So all these 3 terminals we have to clear. So CLR P2.0, P2.1, P2.1 instructions will use to send the address 000. Then send ALE signal. So first we'll send we'll use instruction clear to send logic 0, and then we'll use instruction set bit P2.4. We can use delay also between this, but without delay also it will work. So address is latch. We'll send a start of conversion signal. Again low to high pulse we have to send on SOC. So clear P2.3 and then set bit P2.3. Now after this we have to check whether conversion is over or not. So to check it, we'll use instruction JB. Jump if bit is set. So which bit we want to check? P2.6. So if this bit is set, that means if this pin is at 1, then go to label L1. So L1 label is given to same instruction. So if this bit is 1, it will continuously execute this instruction till it becomes 0. If this bit is 0, then it will come out of loop and then we'll send output enable signal. For that, we have to send again low to high pulse. So we'll clear P2.3 and then set P2.3. So set bit P2.3. So now digital output is available on port P1. We'll read it. For that we'll use instruction move A comma P1. So read the data from P1, send it in accumulator, and now send this accumulator data on port P3 where LEDs are connected. So according to this data, LED will glow or it will be remain off.